Well, Houston, it appears we have a problem. This has worked every other time. Let's try refreshing it once more. So this time the router has responded with the correct content because we wanted to go back and forth so we could show you what it looks like in both scenarios. We'll refresh it one more time. We got the wrong content again. Actually, I see a TK error in the background, so I apologize. X forwarding has broken, but that TK error was TK trying to pop up the box. So the browser did catch the error, and if TK were cooperating, we would have seen that it alerted us to the bad content. So let's go back to the slides. And that is a very simple example of intrinsic security in XIA. All right, third, we want to show you how one might go about deploying XIA on top of an IP network. So at this point, I have a confession to make. I've been hiding something from you all morning. There is no link between Houston and CMU. In fact, there's just the IP internet. Actually, the IP internet too, but for the purposes of this demo, it's the same. Now, how have we been communicating with the web server, which is in our XIA network on Genie, if CMU and our XIA network are not connected directly? Well, we've actually introduced a new principal type, the IPv4 principal type. Now, an IPv4 ID, or a 4 ID for short, is the IP address of an ingress router to a remote XIA cloud. So let's put the IP addresses up. So the router in Houston is actually a dual stack router. It speaks XIA and it speaks IP. Its IP facing port has this IP address. Our node at CMU has that IP address, and we're going to use these in 4 IDs to achieve communication between these disjoint XIA clouds. So I told you that this was the DAG that the web browser was using to request content from the web server. In fact, this is the DAG we were using. We had an additional fallback that included the 4 ID, which is the IPv4 address of the router in Houston. So when the XIA, when the web browser on our host goes to forward it, it says, I don't have entries for this domain, this host, or this CID, so I'm going to fall back and send this packet into the IP network. It'll travel through IP. It'll arrive at Houston. The router in Houston will see that this packet is addressed to me, pull out the XIA packet inside, and forward it into the XIA network running on Genie. Now, how do responses get back to us? Well, we do the same thing. We add a 4 ID fallback to the source DAG with our own IP address. Now, I want to stress that this is not a statically configured tunnel. This is dynamic per packet encapsulation. The only piece of information that the host at CMU needed to know was how to contact an XIA name server. The XIA name server responded with that DAG on the left, which included the 4 ID that the web browser needed to reach this particular XIA network. We could run a different application on the host at CMU that wanted to talk to a different disjoint XIA network, and the name server could give us a DAG with a different 4 ID in it to get those packets there. So that in a nutshell is how we can think about deploying XIA on top of IP. And finally, we just wanted to show off, we have a Wireshark plugin that's really great for debugging your XIA network. So we actually captured a packet trace of exchanges between our web server and our web proxy, and so Matt's just going to pull that up. All right, so this is, this is just a pretty standard looking packet trace in Wireshark, but you see that it recognizes that the protocol is XIP. That's what we call our forwarding protocol. And we can open up the XIP section, and you'll see all of our header fields there, most notably source and destination DAG, so we can expand those and see the DAGs in ASCII format. And this was very helpful in debugging our demos. So that is our Wireshark plugin. So those were the 4 things we wanted to go over with you today, but there is one more thing. Most of the stuff that you saw us do today, you too can do. We have a publicly available XIA prototype. You can download it as a tarball. You can check out our repository on GitHub, or you can download a VM that has our source and the environment already configured for you. On our wiki, we also, of course, have detailed instructions on how to get XIA up and running on Genie, so you can do this yourselves. And all of this and more is available at our homepage here. So that's what we have for you this morning. Thank you.
So that was a wonderful demo. Thanks, David. Thank you, Matt. Thanks, Peter. So we have, we've just seen a really exciting bit of collaboration. We've seen, XIA, which has been using some of the basic underpinnings of Genie to run a extended series of experiments over time. We've seen them extend this network out into a federated, non-Genie set of resources, the B nodes running in Tokyo. And, I won't say it was easy, but, it did work, and it took a finite amount of time. So this is a really neat thing to see. I realize we have really cut very badly into our break. Let's take just 15 minutes and come right back, because I promise you the second half of this plenary is every bit as good as the first half was. So thanks very much.
Thank you very much. So let me go ahead and get started here. Yeah, so basically what I'm going to talk about is a test bed that I'm sure many of you, at least those of you who've attended this conference before, have heard a lot about, which is a Seattle test bed. It's a project that I started about 4 years ago, and is a big group project that's had a lot of people from different universities and institutions contribute to this. So overall, first thing, for those of you who don't know, what is Seattle? So the kind of one-liner conceptual thing here is it's kind of like a peer-to-peer Planet Lab or EC2 or Google App Engine or something like that. So it's a little bit of software anybody can go and they can download and run on just about any type of computing device, whether it's a laptop, a desktop, a mobile phone, tablets. We have lots of people all around the world running this software. And then other people can go and utilize those resources much like they would use something like Planet Lab. So let me give you, a little more detail here. So we have these end users who decide that they want to run our software and become a node. It's a little bit of software that you install. It runs in the background. It has performance and security isolation, so you don't have to worry about bad things happening or it slowing your system down. And it really doesn't need you to mess around with it. You kind of install it and forget about it. And it runs on lots of different types of devices, as you can see here. There will be a link I can show you where if you're interested you can go and run it, but it's really easy to install and participate in. And the way that this is often used in the classroom, for those of you who are educators and are thinking, hey, I want to go and improve my networking classes, I want to improve my security classes, I want to improve my operating system classes by giving students more hands-on experience with a platform that's very easy to use. So the way this works is students go to a clearinghouse that we have set up, they request resources, and then they can easily go and fire up programs that run on computers all around the world, not just machines at your university. So it's really easy, as you'll see in a minute, to do things in a global sense. It's easy for students to go and also test things locally if they want, and especially for some of the things like some of the security classes that use our platform, they mostly do things locally rather than use things in a global sense. And basically, the way that our testbed grows is we have people who use it install the software if they like. It's completely optional, you don't need to. But we get enough sort of altruistic donations that our testbed grows. We give you 10 virtual machines just for registering an account on our platform. If you want more than 10 virtual machines, please install it on some systems that you have. If you need much more than you can put it on, then send us an email. Don't go and write a script and register like 500 accounts or something. We're nice people, so just come and ask us, and we basically always say yes if you need more virtual machines. All right, and I said briefly about this, it's an environment that people run code in that has performance isolation, it's secure, there's a node manager for remote control, it's portable to different environments so your students don't have to worry, like does my code run correctly on Android versus iOS versus Windows, that's all handled for you. And it's a programming language VM based upon Python that the overwhelming experience that we've had, the overwhelming feedback we've had from everybody is this platform is super easy to use. So now let me just go through and show you this. This is a real thing out there ready. It's being used a lot right now, so don't be afraid to try along or play with this yourself. So I'm at the main site here, and I'm going to go through and register a new account specifically just to do a demo here. So we'll call this GEC15 demo, type in a password, and then some affiliation. And by the way, the affiliation and other things like this, we don't check any of this. This is just if I would decide I want my password reset at some future point, then this will be used. Otherwise, we don't send you emails or anything, and we don't care about your affiliation or anything like that. It's just for us to have so we have some idea about who might be using it. And now I'm ready to go. I'm logged in, and right now I'm ready to go and get virtual machines, so I'll go ahead and do that. I'll go ahead and grab 10 virtual machines on computers all around the world. And I think if you're an instructor now, you should be thinking to yourself, look at how easy this is. My students could easily do this. There was no setup. Nobody had to go in and enable my account. Nobody had to go in and do anything, to set this up. Right now I have 10 computers all around the world waiting to do my bidding. So what I'm going to do here is I'm going to go and download my credentials here. Oh, and by the way, there's extensive documentation on our website that walks you through all of this in a lot of detail. We have so any of these steps, we've literally had thousands of people go through our wiki pages and tutorials and things. So they're very debugged, very, very easy to use. All right. And so now what I'll do is I'll load in my credentials. And I'm actually going to do something with these computers that I went and acquired. So first thing I'm doing is I'm telling the shell to go and locate computers. You can see it only located 9 of them. You can tell these are real computers like laptops, phones, and things. So one of these systems may have been turned off or shut down in the meantime. If I wanted to, I could go in here and remove it and get a different one. And I can go in here and figure out maybe where are these computers at. Well, that's a really boring list. So I have a whole bunch of nodes in the US, one in Canada, France, and Germany. I'm not too happy with that, so maybe I'll go and I'll grab another 10 or so at random so I can get maybe a more geographically diverse distribution of nodes. Once again, it comes up rather quickly. And now I'm asking the shell, okay, go and find places where your credentials will work. And I can go in here and ask for the location of these, and this is not great, but is a little better. So now I have a node in China, Poland, Thailand, as well as some US nodes. I can go here and I can actually run a program. So I'm going to go and do an all pairs ping program, which is actually part of one of the assignments that we have available for the platform. So right now I've just written out a file that contains the list of IP addresses for the nodes that I'm accessing. And now what I'm going to do is I'm going to go and run this on these nodes. And for those of you who have had students where you've given them some example and you've put a port number in the example handout you gave to them and you found that everybody tried to use the same port, we handle that by restricting the port number. So I know this port number is going to be unique to all the virtual machines that I get here. So what this has done right now is this has gone on these machines that I have, and it's actually started my code running. So I can take one of these IP addresses, and it was that easy for me to go and deploy this program that shows an adjacency matrix. It looks like the left side's a little cut off here. So if I refresh this, you'll see that the numbers update. So I went from an unauthenticated user about 5 minutes ago to running code on random computers around the world. And the steps I went through are actually part of one of the assignments that we have available on our website. We have a bunch of pre-made materials for educators that go through, and these are assignment sheets that walk you and your students through in detail, like exactly how to go through and perform a series of actions, and they're focused on a specific learning goal. Like this one teaches about non-transitive connectivity and shows the students what it's like to be behind a NAT. We have all the traditional networking assignments you'll see, as well as some security assignments, and we're in the process of using this platform in an operating systems class now. So we hope to have those assignments up and ready in the near future. So, okay, so I hope this gave you some idea about just how quick and easy it is for you and your students to use this platform. Seattle was released in spring of 2009, so it's a very new platform. We actually got our first funding from the Genie project, which we're very grateful for. It has to date been used already in 25 classes at universities all over the world, and there's actually 7 classes this semester that are using our platform. The overwhelming feedback from people is they love it. They love the platform. They love how easy it is to use. We've had lots of people from everything from we had somebody at a 2-year community college use the platform. We've had people at 4-year teaching schools use it. We've had top research universities. It's been a mix, and they say it's easy for the students to use. They love it, et cetera. And we're very grateful for all the support we've had from different people in the community. Different educational groups have endorsed our platform and been very positive about it. And we're getting assignments for using our platform incorporated into the next revision of the Caros and Ross networking book, which is the most popular networking book. Okay, and people are also using this for research. So if you have interest, if you'd like to be able to use a platform that has phones and tablets and things like this for your research, please come and talk to me, because the internet is much more diverse than what you get with Genie. Genie is absolutely excellent at giving you high bandwidth, stable, programmable links. But if you want to know what the real internet looks like, then you have to go to the end host. So, okay. So there's a bunch of people that I would like to thank, or a bunch of groups that played a big part in this. And I'm not going to go through and acknowledge everybody, but this is very much a team effort. We've had more than 100 developers commit code that made it into our code base. And we've had lots of different groups and organizations spend a lot of time and energy to make this a reality. So this is not just something that you can install and run as a platform, but if you want to contribute to the overall community and help to build it and do things, then I strongly encourage you to do so. So to summarize, we have this test bed called Seattle. It's a real system deployed all around the world. It's been in continuous use for the last few years. It has geographic diversity, real device diversity, real networks, and so on. It's very easy for you to run it, to do things with it, and it's really a very robust and battle-tested educational platform that I encourage you guys to try out. It's free, safe, and simple to use. You do not have to install Seattle nodes in order to use it. We'd like you to, or at least we'd like you to ask your students if they don't mind, if they feel like they would like to install it on their home machine, then that would be great. No pressure or anything. But we have thousands of installs, thousands of developers, thousands of VMs available. So it's all ready to go, and there's more than a dozen assignments, everything from networking, distributed systems, cloud classes, security, and operating systems. So there's a URL there, and thank you for your time and your attention.
Thank you very much, Justin. Ashish, our next presenter is Ashish Vulimiri from the University of Illinois. For those of you who've been coming to GECs for a while, you may remember Ashish from, I guess it would be 2 years ago now, at GEC 9 in Washington, when he was just getting started doing experiments with Genie. We're well past that now. And Ashish will talk about some relatively recent results and some new experiments he's been doing. And this is a preview of a presentation he'll be giving at HotNets next week. So you guys saw it here first.
Okay, hello. Today I'll be talking about some work we've done arguing for redundancy as a technique for improving latency. This is joint work with Oliver Michel, who was an intern with us at UIUC last summer, Brighton Godfrey, my advisor at UIUC, and Scott Schenker. Latency is important to humans. Studies at Amazon and Bing have shown that delays on the order of a few hundreds of milliseconds could cause their expected revenue to go down by about 1%. And a study at Google found that a 400 millisecond delay could cause the search volume to go down by about 0.6% each day, which translates to 2 million fewer queries per day. And there have been several human-computer interaction studies showing that delays on the order of tens or hundreds of milliseconds can have a significant impact on users' quality of experience. This is an example from a racing game in which the authors found that just 50 milliseconds of added delay could cause users' performance to go down by about 17%. So having a low delay is critical to the quality of users' experience. But controlling latency, especially the tail of the latency distribution, is a very difficult problem for two reasons. First, some amount of performance uncertainty is unavoidable in any large system. Momentarily high latency could be caused by any of several factors. Some object might be missing from a cache. A network link might be congested. A disk lookup might slow down because the drive head needs to move. Or a DNS name might force a recursive lookup going all the way to the authoritative name server, and so on. Controlling for every possible cause of high latency in a large system is going to be impossible, or at least somewhere between difficult and impossible. Second, many of today's applications tend to be highly distributed in nature. They tend to be structured as the combination of many independent tasks, each of which has a very tight latency deadline. This is an example of one such application structure, the partition aggregate pattern from the data center TCP paper from 2 years ago. These dependencies mean that a delay in any one task can end up having a significant impact on the latency of the entire application. So this combination of factors, pervasive performance uncertainty, and an application structure that tends to magnify the effects of this uncertainty mean that controlling latency is a fundamentally difficult problem. But what we do understand how to do relatively well is how to scale throughput. We know how to augment a system with extra capacity in order to improve its throughput. What I'll be talking about today is one technique for converting or spending some amount of throughput in order to improve latency, redundancy. The basic idea is very simple. Initiate multiple copies of latency-sensitive operations, ideally using distinct sets of resources. So for example, last year, you might send multiple copies of the same query to different servers in parallel. Or you might send multiple copies of the same packet on the same or on different paths. The reason this helps is that it moderates the tail of the latency distribution. Some amount of performance uncertainty is likely unavoidable in any system, as we discussed 2 slides ago. And redundancy helps by masking the effects of this uncertainty. Redundancy is not in itself a novel idea. Its use has been explored in the past in a variety of settings. But the use of redundancy tends to be the exception, not the rule. And in particular, redundancy tends to be avoided in the wide area internet. Our point is that this is a missed opportunity, that redundancy can be used much more widely than it currently is. Today, I'll be presenting an argument for the benefits of redundancy. I'll be making this argument in 3 parts. First, I'll present an intuitive justification for why the overhead from redundancy should be tolerably low. Then I'll establish a benchmark, quantifying when the benefits due to redundancy outweigh the cost of the overhead it adds. And finally, I'll discuss examples of several applications that clear this benchmark comfortably. Let's start with overhead. Intuitively, latency-sensitive tasks should be small. If a flow, for example, is large, then its completion time will be determined primarily by the average throughput it can get. The latency on the path won't have that much of an impact. So this means that if a flow is latency sensitive, it is likely to be small. which means that the overhead from replicating it should also be correspondingly small. To confirm this, we looked at flow size measurements from a variety of sources and estimated the overhead that would result if the smallest X% of all flows were to be duplicated. And as you can see, the overhead grows very slowly with X. You could, for example, replicate the smallest 33% of all flows with a less than 2% increase in overhead. Now let's establish a benchmark quantifying when the cost of this overhead is less than the benefit due to redundancy. The benefit can be broken down as the product of two components. The total reduction in latency times the value that a 1 millisecond reduction in latency has to the end user. So basically, total performance improvement times the value of 1 unit of performance improvement. Now we'll try to estimate the values of each of these quantities. We start with the value of time. That is, how much value does a 1 millisecond reduction in latency have to the end user? This is very hard to quantify. It depends on both the end user and the application. But as a first approximation, we just use the US median wage. There are problems with doing this, but it's a reasonable starting point. And as we'll see later, the difference between cost and benefit is likely to be orders of magnitude anyway. So having a precise value here is not that important. Next, cost of overhead. To determine the cost of overhead, we looked at the bandwidth charges charged by several providers. We have both server-side and client-side costs. And the key takeaways here are that, one, server-side costs tend to be dominated by client-side costs. So the bandwidth usually tends to be a lot more expensive for the clients than it is for the servers. Second, bandwidth is the most expensive on a cell phone data plan, where it costs about $65 for every gigabyte of traffic that you send. Now, if we take these numbers and plug these values in, we find that what we need is this. Basically, as long as redundancy can reduce latency by 10 milliseconds for every extra kilobyte of traffic that you send, its use is always going to be worth it, even on the most expensive cell phone plan. DSL bandwidth is cheaper, so the corresponding target is also much smaller at 0.03 milliseconds per kilobyte if you're on a DSL plan. So these are our performance targets. Now we'll discuss examples of 3 applications in which the observed performance is significantly larger than both these thresholds. We start with DNS. Here we want to evaluate the performance benefits from sending multiple copies of DNS queries to different servers in parallel. To evaluate this, we collected measurements on Planet Lab. We ran a 2-stage experiment. We started with a list of DNS servers at each node, the local DNS server, as well as some set of publicly accessible DNS servers. In stage 1, we measured the average performance of each of these servers and then ranked them in the order of their average performance. And then in stage 2, we tested different levels of replication. If we had 4 DNS servers, we would send 1, 2, 3, or 4 copies of every query. And when sending these queries, they would go to the servers in the ranked order. So when sending k copies of a query, they would go to the k best DNS servers. That is the first k entries on that list. We ran this on Planet Lab with 20 Planet Lab nodes and a list of 10 DNS servers at each node. And this is what we found. The plot shows the fraction of queries that require longer than a given response time threshold to be processed. As you can see, the 99th percentile latency goes down from 1.4 seconds to less than 1 second if you contact just 2 servers instead of 1. And if you contact 10 servers in parallel, then it goes down even further to 0.5 seconds. Now, if you take these improvement numbers and normalize by the cost of overhead, then it turns out that the optimal thing to do is to contact 5 servers for each query if you're on a cell phone plan, and to contact 10 servers for each query if you're on a DSL plan. The corresponding latency improvements are 90 milliseconds and 100 milliseconds. Now, the incremental improvement from sending 10 copies instead of 5 is not that large. It's only 10 milliseconds at the cost of twice the overhead. But it still makes economic sense because, relatively speaking, DSL bandwidth is very cheap. Now, our second application. multipath overlay. Here we want to evaluate the benefits from sending multiple copies of packets on different overlay paths. And here, as in DNS, we tested this using a Planet Lab experiment. The set of topologies we tested is not large enough for these results to be representative. But what they do demonstrate is that there are valid scenarios in which redundancy helps. So we used a very simple one-hop overlay topology. Packets go from the source to one intermediate node to the destination node. And we tested data rates of between 32 and 56 kilobits per second. Both the topology and the data rate match what is seen in VoIP applications such as Skype. Skype uses a similar topology to punch holes in firewalls and NATs. When we ran this experiment on Planet Lab, this is what we found. Redundancy significantly improves the performance in the tail. The 99.9th percentile latency goes down from more than 1 second to less than 150 milliseconds when you send 2 copies of each packet instead of 1. And if you take these improvement numbers and normalize by the cost of overhead, then it turns out that these are the latency savings that you get compared to the targets that we established earlier. The numbers here are not as impressive as they were in DNS. This seems to say, for example, that the improvement in the mean is not worth the cost of the added overhead if you're on an expensive cell phone plan. But the improvement in the tail is still quite significant. And again, it always makes sense to replicate traffic if you're on a cheaper DSL plan, even in the mean. Again, as I noted earlier, these results are not necessarily representative, merely indicative. Okay, so far we've been considering the question of when it makes sense for an individual user to selfishly decide whether it should replicate its traffic or not. Now we take the whole system view. That is, we see what happens if every user in the system replicates its traffic. We did a queuing analysis, and it turns out that what we should expect is a sort of thresholding effect. Essentially, there is a threshold load such that above the threshold, the cost of the extra load added by redundancy overwhelms any performance improvement that you see. But below this threshold, redundancy always improves performance, even if every user in the system replicates their traffic. So the key point is that you can lower bound this threshold. It is at least 30% load. The result that we have now makes a low variance assumption on the service time, but there are strong indications that this is an assumption that that we should be able to eliminate. So what this says is that there is a level of provisioning such that if the system is provisioned to that level, then redundancy always improves performance, even if every user in the system replicates their traffic. And the threshold should be much higher than 30% in a real system where only a subset of the traffic should be latency sensitive. We were able to confirm this thresholding effect in a real system, a deployment of a distributed cache on Memcached. Note that we observe the same trend, and we observe a similar level of performance improvement as predicted by the analysis. So, to summarize, we had one basic idea, which was that redundancy could help improve latency, which was applicable in a range of scenarios. The experiments that we needed to evaluate the benefits had different requirements based on the application scenario we were considering. And in each experiment, we chose the Genie resources that were appropriate to the set of requirements that we had. And the results that we found demonstrate that redundancy is a useful technique for converting a small amount of extra capacity into a latency improvement. Further details are in our paper, which will be presented at Hotnets next week. Thank you.
Thank you very much, Ashish. It's really great stuff. Whoops. So I'd like to introduce Prasad Gupta from Ohio State University, who's going to talk about some uses of OpenFlow in managing virtual desktops. I think we get both results and a demo.
I hope so.
Excellent.
How many users are happily screaming or complaining and screaming. That will give you a net utility loss, right? So you basically have added faults and load, and so in this case it sort of goes down. In this case, it goes up. Okay, so it's a random simulation. The numbers vary, but essentially it goes down and goes up, right? So based on loads and faults. So the idea is that, so in this case, actually, I could show it actually went down. But again, it depends on the number of requests you use, and it's a random simulation, the schemes. And again, there are different schemes you can plug in, and that's the whole point. So if you have this platform, as a researcher, you could be testing new schemes of provisioning and placement, least cost, least load, utility directed versus some sort of a market-based approach. You can study the dynamics of the cloud, of how, as requests come in and go, what happens to the net utility, and how your design of the cloud is working. And in terms of the education use case, I think there's a very good set of rich education use cases. And we started doing this with Sonia Fahmi's group, and we're almost there to sort of get something out in writing on a wiki. But really what we're looking at is getting students to understand server-side adaptation. So if you have thin clients and remote applications in non-ideal network conditions, instead of going and making multiple round trips, you could do something smart on the server side. So you reduce the round trips, you can improve the user experience. And so that's a sort of a classroom example we're working on. The other one is the client-side adaptation, where students understand that different encodings have different user experience, if it's an image or a video or a text file, and they're able to sort of appreciate, measure, and know how to adapt intelligently the thin client encoding so you can get best user experience for a different application profile. So that's another use case for education. And now to the main OpenFlow demo. We have about 4 minutes. We'll quickly go through it. We use a concept of a marker packet that identifies when a request comes in, what profile it is and where to place it. And it has certain information of what group it is, and how all of that works is, in essence, there are the 4 pieces that we have to orchestrate: the desktop, on the server side, the OpenFlow switch, the controller, and the client. And so the requests, before they come in, the switches basically register with the controller, and the actual thin client connects to the cloud, and it goes to the OpenFlow switch that points the packet back to the controller that says, now we're going to provision based on the profile, the amount of system resources and the network resources, and that provisioning happens, and the thin client directly connects to the virtual desktop, and it all works. So this is all set up on the fly. It can be done proactively, where you've put the flow tables. It could be run reactively when events happen. So that's what is the demonstration. Sudarshan will show you in the next couple of minutes. So here's the slides that we have with 2 data centers, one at Ohio State, one at the University of Utah. And we have various protogeny, wide area protogeny nodes acting as thin clients, and we've implemented basically this architecture that I just showed you of how we provision and place. And there is a very simplistic demo. We wanted to keep all the moving parts to the minimum. There's one thin client and then some cross traffic that's congesting at Atlanta. And when we load balance it, the cross traffic is rerouted and the experience is better. So, so it's congestion-free path. So that's what we'll show you right now. So step 1. He's basically requesting all the thin clients to connect to the cloud. And in this case, you can see we successfully got some application running, and if we press this play, it will play. And so it's consuming some bandwidth. There's no cross traffic, and so everything is good. All cute animals show up, and the videos are happy, and all the applications are responsive. By the way, it worked many times yesterday, so hopefully it'll work today. There you go. So it won't be super nice because of resources at client and this other logistics, but it will play a video. That's the hope. All right. Are you connected wireless or wired? You want to connect to wire? So it worked on wireless, so it was a working demo. But anyway, in the essence of time, I'll sort of go forward if you can get it. Okay. So the point is that a video was running, and then we added the cross-traffic flows, and the flow table obviously changes with the cross-traffic. We've instantiated that in the. Try it again. So at that point, if the video worked, now he's trying to do the cross-traffic. So he's introducing the cross-traffic, and all of this is actually talking to the Genie slice. As you can see, it's still rough. We've got a lot of work to do, but the point, hopefully you're able to get what we're trying to say here. And at this point, he's introduced the cross-traffic, so this video essentially freezes, and you basically can't use any of the interactive applications in the desktop. So that's kind of where the cross-traffic is getting its share, but the application is squeezed out. The last part is when we do the load balancing, when we reroute the flow using OpenFlow, the application sort of gets its fair share, and cross-traffic is also happy. So that's the demo. I know I've run out of time, so thank you.
Thanks, Prasad. Thanks, Siddhartha. So I want to apologize for the video confusion, but there was a very cool demo going on back there, right? We saw this service capability installed in a Genie slice, and we saw researchers actually using that to validate that their service works according to their designs, and then to test it in the presence of competing traffic. So there's a lot going on in there.